So anyway, as a beginning, you will see also that our work is financed partially by the Greek government and the European Union. Just saying, just in case there are some sort of conflicts of interest. So our idea, in a nutshell, what we have done. First of all, I need to be clear that we are far more specific than the approach of Professor Taburazis. So we're going to discuss about a very specific network that we are more or less started developing a couple of months before. What we will demonstrate here is mainly the architecture and the learning algorithm. With regards to the results, we are still at the stage of, let's say, proof of concept or proof of principle state. So anyway, our idea in a nutshell is having what was mentioned previously, that is a deep network, what we can see on the right. But instead of having the usual approach of labels and targets and the usual issues that usually happen in the deep or not that deep realm, we have the approach. We were thinking if we were in position anyway to build a network, actually not build it, train it, because that's the difficult part. I mean, the weights, the biases, and the deltas. Train it without having to resort in label or target information. So in a sense, and following what was mentioned previously, we were thinking of actually building, in terms of, let's say, the biologically inspired stuff, something more similar to what's happening in our brain. If you think about it, you do not always have a teacher, a tutor, or your parents telling you what to do and what not to do. Many things are learned, as said previously, automatically. So our approach, because you might hear me using the acronym quite frequently, is called the SOCOM, the Self-Organizing Map of Convolutional Network, of convolutional layers. And it's actually a prototype that's in position to carry out unsupervised classification and clustering tasks based upon higher level representations that are produced by its underlying convolutional deep architecture. And as I said previously, without necessitating obviously any type of target or label information. Possibly I've also referred to this thing, but the most common bottleneck encountered in many deep learning approaches like CNNs is this requirement of big labeled data sets. Even for being in position to classify or categorize a couple of grayscale images, you might need something like 50 or 60,000 samples, which is a huge number. And it's a huge number because if we are talking about real world tasks, for instance, if we were talking about the task previously mentioned with the nuclear reactors, somebody will have to semi-manually create and curate these datasets, which could be quite costly and time-consuming procedure. And usually along these procedures do not end up being even finalized properly, and you are left in the middle way. And so what we are going to discuss about in a minute is actually, we're not obviously going to solve all the problems of deep neural networks and artificial intelligence, but we're more focusing in on a more specific paradigm. And this paradigm is actually a hybridization of the convolutional neural network approach and the self-organizing maps. Briefly, the self-organizing maps, as I mentioned previously, I won't go into detail because we have discussed about these things. The self-organizing maps were actually inspired by Professor Kohonen already 30 or more plus years ago. And they were an approach to computationally approximate what was happening in the cortexes of our brain, in particular the outer thin layer that's around 1 to 2 millimeters. I mean, if you have been to a medical school, you have seen this gray matter that's on the outer surface of our brain. And so what he initially came up with was the self-organizing map and the resulting algorithm. You can see here a visualization that's by Michael Hickman. He has a couple of really nice visualizations of these things. And what we can see here is a two-dimensional self-organizing map. Okay, it might seem nice in terms of graphic, but it's a quite simple example because we are talking about a mere two-dimensional space that whereupon we're trying to fit a mesh of tunable neurons. Anyway, the approach in the self-organizing map, or the strategy behind building the network, is that whenever you have an input sample, in this case, as I said, it's a two-dimensional sample, but can be whatever. So for instance, in our case, the inputs are the higher level representations produced by convolutional neural networks. You can feed these things to the neural output layer. And what happens here is a competition, a first stage competition between the neurons, so you can find the one that's firing optimally. Subsequently, this neuron that fires optimally adjusts the neurons in its vicinity or neighborhood, as you might have heard in the past or by some approaches. And what happens in the long run, or eventually, you are hoping that at least this best responding neuron and the ones around it are actually going to be more optimally fitting in the case where this sample in the future appears again. Weirdly enough, despite the fact that this procedure could sound or appear quite lamer and straightforward, it does produce results, and it's producing, in some certain cases, semi-state of the art results, but because it's obviously restricted by its two-dimensional or three-dimensional idea or plane of the output, it cannot go to far more complex stuff, because obviously we as humans are not in position to interpret results beyond the 2 and 3 dimensions. I mean, interpret them in terms of some sort of visual translation. So I won't go into detail into the remaining stuff, but as we have discussed, the idea behind neural networks is trying to find some sort of bio-inspired idea behind the neuron sense, and trying to more or less make a computational model of this thing. Obviously, as you may already well know, this is not a one-to-one correspondence, but something like, I would say, a more macroscopic approach. So what happens in terms of the math, let's say, something like that, where we aggregate or sum up the inputs, we weight them, and after we have estimated some sort of potential, we pass it through a non-linear function. And the non-linear part is really important because, in particular, because we are talking about a quite substantial number of hidden layers. Having more than 2 or 3 hidden layers without the non-linear activation functions mathematically is equivalent to having just a single layer input, a single hidden layer, so it wouldn't work. So at this point, I might have to ask you if you try to raise the volume in your computer, because that's a small sample video from 1959, which more or less experimentally proves what we are about to talk about, the fact that humans and possibly our visual perception, and as a result, what we're trying to do with convolutional neural networks is pretty similar to what's happening in the brain, in the brains in particular of in the visual, let's say, computation and integration of the information. So what these two guys have done, professors, have done in the past, is that they planted the electrodes onto a cat, and they were trying to see if these neurons in the cortex were firing with regard to what the cat was seeing. So let me give it a just a minute video. Let's try to follow it, and afterwards I will make a small comment on it.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
So, what the guys realized, as you have possibly heard, is that only if a line falls on the retina and the line has a particular orientation, position, or something similar, then there seems to be some sort of firing. As a result, the guys, the first researchers involved in the convolutional neural network, let's say, adventure, decided to follow a quite similar approach. That is, why not try to have a model that in the very beginning, as you see at the bottom, is in position to differentiate or be in position to identify edges, and subsequently, as we move up, trying to build simple shapes, as you can see, for instance, the lines that we see around here, and as we move up, possibly be also in position to differentiate objects, since objects are actually summations or agglomerations of shapes, as you can see, the noses, the eyes, and so forth. And at the very, very, very top layer, one can defensively claim that he might be in position to identify faces, cars, and things like that. So, by following this approach, what they actually did was trying to build layers or simply non-linear constellations of neurons so that they could model this approach. And actually, they have been quite successful in this thing. And the interesting part, at least with regards to what we are discussing right now, is that the images that you can see here are not images that have been artificially being created by some sort of graphic artist or something like that, but these are the actual images that can be seen if a proper visualization method is applied per layer in a convolutional neural network. And this is quite impressive, at least with regards to my criteria. So, let's go to our model. As we have seen in the beginning, our model has obviously an input layer, an output layer that's consisted of an arrangement, a 2- or 3-dimensional arrangement of neurons. And in between, we have the usual components of the convolutional neural networks, that is convolutional layers, which more or less consist of a set or bank of tunable filters. And despite their usually small size, every of one of these filters extends to the full depth of the input volume. And as such, during the forward propagation, each filter slides along the width and the height of the input volume by performing convolutions. Afterwards, that's the one that can be seen in the middle left part of the image. Afterwards, at certain positions, we have the pooling layer. What more or less does the pooling layer? It is trying to bring down the complexity and impose sparsity on our networks. After, during the higher levels of our network, we have the fully connected layers that You can see around here. And what they are doing, they are actually densely connected layers that are identical to the layers of the standard MLPs that have been discussed previously, but obviously in this case they are building upon not the mere and simple inputs that we are feeding to the network, but on the higher representations that are actually produced by the convolutional neural network. And as I have discussed, at the end, we have a some lattice of topologically arranged neurons that act as the input, as the output layer. Each of these neurons receives the activations of every unit in the last fully connected layer, and the magnitude of each neuron's activations is based on usually the Euclidean distance. And after appropriately weighting this thing, we can have the firing or the clustering output of the network. So if you allow me, in terms of, let's say, what's our objective visually, what we try to do is actually have our input, that's for instance the image of letter A in this case, start building our convolutional neural networks through the convolutions, the pooling, and then the application of non-linear functions like the ReLU that we can see in the video on the left. And afterwards, after we have all these higher level representations or CNN features or CNN codes as they usually refer to them, we're aiming to have some sort of lattice fitted over these results so as to be in position not to classify, for instance, images, but to group and cluster them according to their intrinsic attributes and characteristics. In order to do this, the first part, possibly you know that the easy part in neural networks is the forward pass. You just connect the components, you feed the inputs, and if the weights were tuned magically, then you would have the output. The problem is that this magic part does not happen. You could have automated the procedures, but still you need to define the equations and come up with the learning and this algorithms and the specifics of this thing. So the problem, and that's why not that many approaches that try to combine self-organizing maps and convolutional neural networks exist, is that we are lacking the link between training the output layer and training the rest of the CNN. The rest of the CNN can be easily trained with backpropagation. Unfortunately, or mathematically, to be more precise, backpropagation needs functions that can be differentiable. The problem is that the learning approach or the linear learning strategy of the self-organizing map, as I have shown previously, is not based on some full mathematically proven and stringent approach, and definitely is not differentiable. So what we have done, and actually we are still trying to improve and refine, is come up with a different energy cost or loss function, the one that can be seen here. I'm not going to go into details of this thing, you can check the paper, but the idea is to be in position to have a full-scale backpropagation starting from the output layer, going downwards up to the first hidden layer, that is this yellow part over here. The good thing, nevertheless, is that at least the two big players in the AI neural network field, that is PyTorch and TensorFlow, provide the means and the algorithmic and mathematical implementation of at least a big percentage of the backpropagation stuff, that is through their Torch, Autograd, and TF gradient tape libraries. So one can be quite confident that what he's doing, at least in terms of let's say code writing or code editing is right and correct. obviously, we have used the first approach. Actually, we have implemented our model on PyTorch, and we have already made parts of this thing publicly available through our Git. And a couple of more words with regards to this thing. So the interesting thing is that we have done this model, or we are proposing this model actually because we believe that the unsupervised research discipline can be benefited by being in position to have more layers. I'm saying this because the majority of self-organizing maps or unsupervised approaches usually have 1 to maximum 3 hidden layers. That is, in terms, let's say, of AI history, they seem to be architecturally stuck somewhere around the 90s. So what we're trying to do is we're actually trying to interject more hidden layers between the input and the output, and as you have seen. And obviously our idea is not novel because some guys, pretty famous actually guys, have managed to do this thing in the past, and what you see over here are the results in the world famous ImageNet classification competition, where, okay, possibly you know this thing, but currently this competition is over because the machines have surpassed human recognition capability already. But anyway, as long as this competition was being carried out, what was seen is and what also Professor Tabouradzis mentioned, that the more layers somebody has, the better results you get. You can see how exponential was the improvement not exponential, how anyway noticeable the improvement was when the number of layers grew exponentially. So with regards to the first proof of concept, proof of principle results that I mentioned previously, our architecture in detail is the one that appears on the top part of the slide. It is an architecture having obviously an input layer, a neural output layer, and in between we have 20 convolutional layers. Obviously, we could, semi-cheat and say that we have more layers, but the essential parts of what's in between the input and the output are the convolutional layers, because as I mentioned previously, max pooling more or less decreases the dimensionality of the tunable parameters, and the ReLU functions just impose some sort of non-linear restrictions to the activations that propagate through the network. Anyway, with regards to the results on the MNIST grayscale dataset, which is, let's say, the entry-level dataset, if somebody wants to discuss or say something about image recognition or some sort of novel or slightly different deep convolutional architecture. The results can be seen in the chart that we have in the table that we show at the bottom. The interesting thing is that despite the fact that we are not getting the best accuracy overall, the interesting thing with regards at least to our approach is that we are in position to achieve this thing without having to resort to any sort of a priori information with regards to labels, targets, or anything about the inputs. We just feed the inputs and nothing more. So you could have some sort of automated procedure consisting of an array of sensors, feed the numbers in the model, and have some sort of meaningful results. That's the first interesting thing. And you can see the difference. That is, our model has around 20 layers. And the next, let's say, even close one has 8. But even more interestingly, we think that we are slightly quite good or quite well performing, because the other approach that's an end-to-end and supervised learning one, that is doesn't need any other information, is around 10% lower in terms of accuracy or purity with regards to its results. So this is, at this part, more or less our presentation is finalized. I don't know if you have any questions, because obviously I have one more slide that's related and not related to the previous ones.
Thank you. Thank you very much. Are you going to show the last slide?
Okay, so yeah. So the last slide, in every presentation that I actually do or present, I add a picture from a very nice landscape containing windsurfing or something like that, because I'm a big fan of the thing. And this is from last summer, a silver sea in a Greek island, something like 200 nautical miles away from the mainland and everything. So thank you very much. For any further details, obviously, you can check our text, and obviously you can contact us by email. Thank you, Dr. Nanga.